in this presentation, I'll be talking about continual learning. So this is one of the research areas that we are working on at IDEAS and CBR. And more specifically, I'm going to talk about the models that continue to learn during test time. So you have your model, which is trained, and during testing, you still try to use some information to basically update your model. And the short outline of this presentation is that I will start with the motivation for doing continual learning. Then I will talk more about test time adaptation. So this is the setting that we are working on. I will show what is currently possible, what are the limitations. And in the last part of the presentation, I will show our work on addressing those limitations. And a lot of my research motivation comes from my experience working on the Amazon Scout project when I was working on the visual recognition part, being responsible for making sure that the robot knows where it can traverse, where it can drive. And we had this model that worked really well on our training data. And then obviously during deployment, different scenarios happened that make the robot didn't work well. So one of my favorite examples is the autumn scenario when we had leaves falling on the ground. And then suddenly the robot didn't know that it can traverse the road. So basically it stopped operating. And in general, if you have some experience in deploying robots or models to the real world, you know that there are many such scenarios when different things happened that you couldn't envision will happen, and probably you don't have those in your training data. And what I also want to say is that it's not only about robotics. In general, if you have your model being deployed to the real world, then sooner or later you will face some kind of distribution shift. So this is an example from the ObjectNet dataset, when on the first column you have images of objects. Those are chairs from like the typical computer vision dataset. So this is the first column, and another columns are images of those objects that you could see those in real world. So they have like different kind of background or different viewpoint. So basically this is kind of a distribution shift, and this is something that causes a huge performance drop for your model. So in this case, the performance when testing on those more real-world images drops by 50%. Okay, and the question that I ask is, can we continue to learn during the deployment? So basically, we have trained our model, and then we see those new images that perhaps come from different data distribution, and then maybe we can still learn at this time to adapt to changes in those data distributions. And this is one of the promises behind the continual learning. So continual learning is about machine learning models that continue to learn after the initial training stage, and then they accumulate knowledge, and at the same time they retain the knowledge that they have learned previously. And the promises here are improved adaptability. So basically, by continuing to learn, you also continue to adapt to perhaps some changes in data distribution. Another thing is reduced catastrophic forgetting. So this is something that is quite important these days with large foundation models. Then continual learning is about data efficiency, because when learning new tasks or new classes, for example, we try to use as little data as possible from what we have previously seen. And then at the end, it's also about bringing capabilities of machine learning models closer to what, how does the learning in humans look like. And in general, there are many different flavors of continual learning, many different scenarios. And the one that I am talking about today is about continual test time adaptation. And this is the setting. So basically, we have some model, which is pre-trained on some source data, which, for example, can be like images recorded during daytime. And then during testing, the model visits different scenarios, which can be different weather conditions or different lighting conditions. And then the model has to do the online prediction. And also the model has the opportunity to update itself to make the prediction, to improve the predictions. And what is important, we try here to be as general as possible about the changes in data distribution, so it doesn't have to be like robotics or autonomous driving. This could be also like some medical scenario when you are testing your model on different medical data sets from different hospitals, for example. And the question that is here is important, like how can we actually learn the models during test time without any ground truth data, right? Because during test time, we don't have access to this kind of supervision. So how can we actually learn those models? And one of the things that works reasonably well and was proposed in this 10th paper in iClear 2021 was minimizing the entropy. So what they did, they have evaluated their model on the TFAR 100 corrupted benchmark. So this is benchmark that is used to evaluate the robustness of the models. And they have binned the predictions to different buckets based on the predictions entropy. So on the x-axis, you see 10 bars, which based on the entropy. So each of the predictions ends up in one of those buckets. So those predictions that are high confident, they obviously have low entropy. And the predictions that are not so confident, they have higher entropy. And then they plotted the error bars on those. And what you can see is there is a high correlation between the entropy and the error rate. So the idea they had is that maybe you can use entropy minimization during test time to actually optimize your model. Right, so basically during test time we have some predictions, it's called like pseudo labels, and we want the model to be more confident in those predictions. And obviously there is some noise involved in, so there are some tricks how to actually make it work. So in the 10th paper, during this fine-tuning, they only update the batch norm layers, but some other papers, for example, they update the whole model, but then they also do some filtering on those predictions. But this is the general idea that doing the entropy minimization, you are still able to adapt your model to changes in data distribution. Okay, and this is one of the most popular benchmarks for test time adaptation. So this is called ImageNet corrupted. So you have a different type of noises. So this is like Gaussian noise, blur effect, some weather conditions, or some like compression artifacts. So this is like 15 types of different corruptions. And what is happening is that you train your model on clean ImageNet, and then during test time you try to adapt your model to those new conditions. And what is happening, right, is that let's say the clean accuracy, so standard ResNet 50 accuracy on ImageNet is around 90% accuracy, and then the accuracy on those type of corruptions drops to 56%. Right, so this is actually quite interesting because those images look fairly similar to humans, but they make a lot of trouble for the machines, for the algorithms, especially like the accuracy on Gaussian noise and shot noise is around 10 or 20%. And then using those test time adaptation technique, which I have described, we are able to regain a lot of this accuracy. So the accuracy goes back to around 84%. So this is actually quite nice. And the question that we have asked in our research, like, does this progress on this synthetic benchmark? Does it translate to some benchmark that could be more realistic? So this is what we have done in our research. So basically, we have collected data sets from autonomous driving, and we have repurposed those data sets so we could use those in a test time adaptation setting. So we have done 2 such benchmarks, and this is based on the CLAD-C benchmark, and those are some random images from this data set. So what you can see is that obviously there are some images at night or with very low image quality, but at the same time some of those images look fairly similar to probably what you have in your training data. So basically there is a varying level of distribution shift. And we have evaluated current state-of-the-art methods on this benchmark. So here you can see results on 2 data sets. So the blue one is the CFAR corrupted, so this is the synthetic benchmark, and the green one is the CLAD-C, which is the more naturalistic benchmark. And in the first column you have a source model, so this is the model without doing anything. So this is your like pre-trained model or trained model. And then you have 4 adaptation methods. And if you look at the blue one, so this is the synthetic benchmark, you can see that the accuracy improves quite a lot. So this is what I have described just a few slides ago. So the accuracy goes up from 55 to 75%. So that's nice. But if you look at this realistic benchmark, so CLAD-C, the green one, you can see first thing is that the initial accuracy is already fairly well, so it's not bad at the end. But then all of the adaptation methods, so the one thing is that they fail to improve over this source model, and the second thing is that they even like decrease the performance. So this questions whether we should really use those test time adaptation methods at all in this scenario. So this is something that we have started working on, and our intuition was that we should maybe first detect how much the data distribution is changing to what we had in our training data. Right? So idea is that maybe if the distribution data is not changing that much, then maybe we shouldn't do much at this point, and then if this is changing more, then we should adjust to the situation. Right, so first thing we do is that basically we just detect how much the data distribution is changing. So we did fairly simple thing. So we are computing the distance on the batch norm layers statistics. Right, so we use the KL distance between the statistics we have saved from the source model and the statistics we have saved from we have computed, estimated during test time, and this is a symmetric version of the KL distance. So this gives us information how much the data distribution is changing. And then based on that, we actually, because we have discovered that actually there is a lot of trouble happening in the batch norm layers, batch norm statistics, so this is what we want to properly estimate during test time. So what we are doing is that during testing, we are interpolating between the batch norm statistics that we have saved from the source model and those that we calculate during test time. So this is the first equation, and this is parameterized by the beta parameter. So this is the interpolation factor. And actually, this interpolation factor is based on this distance, which I have just shown on the previous slide. So basically, if the data distribution isn't changing much, we are just using more source data statistics. If it's changing a lot, then we are shifting towards test time statistics. And as a last thing, with this beta parameter is smoothed using exponential moving average. This is to make sure that this can work also with small batch sizes. And this is the architecture of our model. So in the middle, you can see the data stream. So this is our testing data. And what we have here in our architecture is like the teacher model and the student model. So this is also something that is known as fast and slow learner. So basically, teacher model is a moving average of the student model. So we use the teacher to do the predictions, which are then used to compute the cross-entropy loss. But then we are updating actually the student model. So this is to provide more stability for this model. And in general, because test time adaptation is very challenging because you don't have any source of supervision during test time, we also include a small replay memory from the source training data. So in this case, we have used 1% of data samples from training time, which are then still used for supervision during testing. And we also do some mix-up data augmentation here, but it's not that important at the end. And going back to the results, so the last column is now our method. So what you can see is that on the synthetic benchmark, we score pretty similar to other methods. But then on this last one, more realistic benchmark, we managed to improve over all of the competing methods. And most importantly, we managed to improve over the source model. So it's not huge, it's around 2 or 3%, but it's much, much better than the other competing methods. And one thing that we have observed is that there are different hyperparameters in those test time adaptation methods. And the hyperparameter that we have is this gamma parameter. So this was here. So this gamma parameter, it decides whether we stick more to the source data statistics or more to the statistics that we compute at test time. And basically, you can see that for those different scenarios, you want to have pretty much different parameters. So for the synthetic benchmark, you want to rely more on the statistics that you have computed at test time, and for the realistic benchmark, you want to stick closer to your statistics computed at training time. Right. So this is, I think, this is something very important, how to actually choose those hyperparameters. So like learning rate, momentum, and some method-specific parameters. So what is happening currently in the research community is that all of the methods, they report the results assuming access to the target labels. So they estimate the parameters using this ground-truth data from test time, which actually you shouldn't do in this scenario. So in general, it's fine for comparing different methods, but at the same time, it's obviously not very realistic. So this is something that we are working on right now. And going to the conclusions, so I have shown that test time adaptation methods, they may improve your model accuracy using some information available at test time. However, it's still there's a lot of research to be done to make those methods more realistic. And what we are working on right now is doing the hyperparameter selection in an online way and scaling this to very long sequences. And as a last slide, just wanted to say there is a poster session today, and there are 3 posters from our PhD students. So if you're interested, you can also go and see our posters. Thank you.